Hello everyone, this is lecture 5 of ComSci 142, Divide and Conquer Algorithms. In today's video, we will discuss the divide and conquer strategy and use it to solve problems like the counting inversions and finding the median. We will also discuss recurrence relations for divide and conquer and the master theorem, which is used to find the running times of divide and conquer algorithms. Okay, so divide and conquer is the first algorithm design paradigm that we'll discuss. After this, we'll also discuss dynamic programming and the greedy strategy. So what is divide and conquer? In divide and conquer, we have three steps: divide, conquer, and merge. The divide step breaks the original problem into sub-problems. A sub-problem is just a smaller instance of the same problem. Okay? And then you divide the sub-problem into sub-problems and so on. So you divide the bigger problems into smaller ones and the smaller ones into even smaller ones. Okay? Next is the conquer step. In the conquer step, we recursively solve the sub-problems. So after the divide step, when we have already broken the original problem into very small sub-problems, we will recursively solve them already. Okay, so this is the conquer step. We will start with the base case, or the tail end of the recursion, or the sub-problem that cannot be divided into a smaller sub-problem anymore. So that's the base case already. Okay, so we'll start here and then use that to solve the sub-problem. So in the base case, the sub-problems become so small that they can be solved trivially. Okay, so for example, if there's only one item left, then you can easily solve the problem for that one because there's only one item, right? So that's the conquer part. Okay, solving the sub-problems. And then the last part is the combine or the merge step, wherein you combine sub-problem solutions to form the original problem's solution. So after solving the smaller sub-problems, you can combine their solutions to form the bigger solution, basically. Okay, so sometimes divide and conquer algorithms only have the divide and conquer step. Sometimes they don't have the merge step or the combine step. Okay, so basically you have this diagram. So the problem is divided into sub-problems, and you can even divide the sub-problems into smaller sub-problems. And after that, when they've already been at the base case, so we will conquer each sub-problem, meaning we'll solve them, and the solutions to sub-problems can be combined to form the solution to the original problem. Okay, so that is divide and conquer, and this is all done recursively. We've already seen some divide and conquer algorithms. We've actually seen about 3 already. Okay, so far we've seen merge sort, which does this. So in merge sort, remember that you divide the input array into half, no? So the left half and the right half, and then divide them further, and then you merge the left and the right later on, okay, to form the sorted version of the array. Okay, so this was the merge part, no? So the left half and the right half, and then for each item, compare the elements of left half and right half, and whichever is the smaller gets copied first to the merged version, right? So merge sort follows divide and conquer. Then you also had quick sort, which was also another divide and conquer algorithm. So in quick sort, remember that we used a pivot to partition the array, and then the items that are less than the pivot goes to the left part, and then the sa right part naman ang items that are greater than the pivot. And then we will use quick sort again on the left half and the right half, or to the left of the pivot and the right of the pivot. Okay, so this is also following the divide and conquer technique, and this one doesn't have any combined step, right? Yeah, so we'll just sort the left and the right half, and then there's no combine. And finally, we also saw binary search earlier. Um, this also follows divide and conquer, wherein we go to the either the left half or the right half. So we'll look at the middle first. If what we're looking for is less than the middle, then we'll go to the left half. Otherwise, we'll go to the right half if greater siya. And then we'll narrow it down to the correct half. So that's also divide and conquer, because you're reducing this problem into half of the problem. So you're either searching in the left half or the right half na lang. And there's also no combined step in this one. Okay, so yeah, those are the three divide and conquer algorithms that we've already encountered in this course. Okay, now let's look at another problem, which is counting inversions, and let's take a look at how we can use divide and conquer to solve this one. But first, what is this problem all about? So in counting inversions, your input is an array of numbers with an arbitrary order, so it could be any random order. The output is, of course, the number of inversions. But what are inversions? So an inversion is a pair of numbers, x and y, where the index of x is less than index of y. That means that x appears before y, but the value of x is greater than the value of y. So x appears before y, but x is bigger than y. Okay, so that is an inversion because they're not in their proper, let's say, placement, or yeah. So if x is bigger, it should appear after, right? If it's sorted, but it's an inversion if it doesn't follow that. Okay, so let's say, for example, in here, if this is the input, okay, so what would be the inversions here? The inversions would be 3, 2, right? So 3 and 2, because 3 appears before 2, but 3 is bigger than 2. We also have 5, 2 here, 5 and 2 here, because 5 appears before 2, but 5 is bigger. And then we also have 5 and 4, right, for the same reason. Okay, now if you write up the sorted version of this one, this would be 1, 2, 3, 4, 5, 6, right? And then if you write also the input version, that's 1, 3, 5, 2, 4, and 6. And then if you match the numbers, let's say 1 to 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. You'll notice that there are some intersections, right? So we have an intersection here, here, and here. And those are exactly our inversions, actually, right? So the intersections are the inversions. So for example, this one is the intersection for 2 and 3, right? 3, 2. This one is the intersection for 5 and 2. This one is the intersection for 5 and 4. Okay? So that is also another way to visualize the inversions. Okay? So now, why are we interested in this problem? So the motivation is you can use inversions as a way to like provide a numerical similarity for two ranked lists. Okay, so you have a ranking of one person and a ranking of another person, and then try to figure out how similar they are. So you can use inversions for this one. Okay, if it's the same ranking, then there would be 0 inversions because, of course, all of them would be aligned, right? And if it's more varied, then there would be more inversions that shows that they are not the same. Okay, so the more inversions, the more varied the rankings. So you can use this for things like collaborative filtering in recommendation systems. Okay, for online shopping, that's when you like suggest other items based on other people's purchase with similar items. So you've probably already seen examples of recommendation systems, right, in online shopping, like sa Shopee, Lazada, or sa even in YouTube, like people who watch this also watched this, right? So that's more or less using some type of collaborative filtering wherein you're trying to figure out what this person is going to like based on how similar your video choices are, or shopping or item choices are, right? So yeah, that would be the motivation or the application for counting inversions. Okay, so now that we have now that we understand what the problem is about, let's try to figure out how to solve it. Okay, so first we'll start with the brute force approach. So you can just check all possible pairs of numbers for a inversion, right? So you can do something like this, like for x from 1 to n, and then for y from x plus 1 to n. So you're doing a double for loop, and just check if a of x is greater than a of y. That means that the value of x is greater than the value of y. Then that is an inversion, so you increment the count, right? But checking all possible pairs will take too long. Like for example, if it's a 6-element array, what is the maximum number of inversions for this one? Now, if it's a 6-element array, what would happen? Okay, so what would be the worst possible case for the inversions? That would be if it's reverse sorted, right? So let's say 6, 5, 4, 3, 2, and then 1. Okay, so how many inversions would there be for 6? Like for 6, it's inverted with 5, 4, 3, 2, and 1. So there are a total of 5 inversions for 6. Then for 5, there would be 1, 2, 3, then 4, right? 4 inversions for 5. For 4, there are 1, 2, 3 inversions. For 3, there are 1, 2 inversions. And for 2, there's only 1 inversion. And for 1, there's nothing, right? So if you add all of this up, that would be 9, 12, 14, 15. So that would be this one, okay? There are 15 elements, 15 inversions in a 6-element array maximum. So how did we get 15? So you'll notice that this is just a sum of numbers from 1 to 5. So basically 1, 2, up to n minus 1, because our n here is 6, right? So up to n minus 1. So this is just sum of the arithmetic series. So that would be n minus 1 plus 1 times n minus 1 over 2. So that would be n minus 1 all over 2, which is 6 times 5 over 2, which is what you get. 30 over 2 is 15, right? So yeah, that's how we got the so but you'll notice that the equation is n times n minus 1 all over 2, which is what? N squared minus n all over 2. So this is still in O of n squared. Okay, so if you just go through all possible pairs in a brute force manner and for inversions, you could finish in O of n squared, okay, which is not what we want. So yeah, this is just what I mentioned earlier. 15 using the n minus 1 over 2. So in the worst case, you have the array in descending order, and everything is an inversion basically, right? So the brute force runs in O of n squared. So can we do better, right? Remember the 3 questions, right? Is it correct? Does it run in reasonable time? And can we do better? So can we do better than O of n squared? Well, of course we can. So to improve on this, the first idea is we will use, of course, divide and conquer. So to do that, let's say that n is the number of items in the array, and we'll call m as the middle, or the half, so n over 2. Okay, we will call inversion. We will classify our inversions into three. So left inversions are inversions wherein both x and y are to the left of the middle. So that means that they are less than or equal to the middle of the array. Okay. The right inversion naman is when you have both x and y, so both numbers that are part of the inversion, appears after the middle. So m is less than x and y. And then finally, we also call something called the split inversion, wherein x is in the left half and then y is in the right half, meaning before and after the middle. Okay, so you have left inversions, right inversions, and split inversions. So for example, if you have something like this, 4, 2, 1, 3, 5, 2, something like this. So the left inversions, so the middle of this would be here, right? This is m. So the left inversions would be 4 and 2. You have 4, 2, 4, 1, and 2, 1. So these are your left inversions. The right inversions naman would be 3, 2, and 5, 2. How about our split inversions? The split inversions would be 4 and 3 here, 4 and 2 here, and then for 2, wala, for 1, wala man. Okay, so these are the split inversions because 4 is here, and then 3 is here, and then 4 is here, and then 2 is here. So 1 is in the left half, 1 is in the right half. Okay, so we'll classify our inversions into left, right, or split inversions. Now, putting that into pseudocode, so we'll do something like this. No, so L would be the left inversions from 1 up to m. Then R would be the count for right inversions for the right half, and then S would be the count for split inversions also. And then we'll just combine L and R and S to get the total number of inversions in the array. Okay, so now our goal is to implement count split inversions in O of n. Okay, this one should run in O of n, and the height of the recursion tree should be O of log n if we're going to divide it into 2. And then we'll be doing O of n work for count split inversions per level if we can implement it in O of n, so that our total running time would be n log n if we do O of n work per level and there are log n levels. Okay, so n times log n would be n log n. That would be our goal. The problem is it's hard to implement count split inversions in linear time, O of n, because as we saw earlier, there could be a quadratic number of split inversions. It could be in n squared, right? Remember earlier when we had 6 items in the array, but there were 15 inversions, right? So it could be quadratic, right? N squared. So for example here, 4, 5, 6, 1, 2, 3. Okay, let's count the number of split inversions here. So the split inversions would be 4, 1 here. So this would be the half, right? So we have the 4 and 1 here, 4 and 2, 4 and 3, 5 and 1, 5 and 2, 5 and 3, 6, 1, 6, 2, 6, 3. So in total, there are 9. Okay, 9 split inversions. And then, how did we get 9? So basically, if n was 6, there were 3 items a half, right? And for each 3 of them, they were involved in 3 on the right as well. So that would be n over 2 times n over 2, which is n squared over 4. But n squared over 4 is still O of n squared. So our number of split inversions could still be in n squared. So it would be difficult to count them in linear time because there are n squared of them. Okay, so now with this, what we'll do is we'll add another idea, which is to piggyback on merge sort. Now, what do we mean by piggyback? We'll basically ride on merge sort to accomplish the counting of split inversions in linear time. Okay, so what we'll do is during the recursion, we will count the inversions and sort the array in the process. Okay, so we'll find out later on that the merge step of merge sort naturally uncovers the split inversions. Okay, so that we can count them in linear time. Okay, so this is actually the clever part of the algorithm. Okay, so remember merge sort, you merge you call merge sort on the left half, you call merge sort on the right half, and then you merge the solutions to get the final answer. And for the count inversions, it has a similar, like our first version had a similar structure, right? So count inversions sa left half, count inversions sa right half, and then count the split inversions. So what we'll do is actually we'll combine these two and we'll get something like this. Okay, so this will be our algorithm for counting inversions. So we'll stop the recursion if n is equal to 1 already, meaning there's only one item in the array, because we cannot divide that further. If it's only 1, then we'll return that array, and there are 0 inversions in a singular array, right? If it's a singleton. And then we'll get m, which is n over 2, get the floor of that, so that's the halfway point. And then we'll sort and count the inversions of the left half. So b would be the sorted version, l would be the count. And then do the same for the right half. And then we'll merge and count the split inversions using the merged version of the left and the right array. And then d would be the merged version, and then s would be the split. So we get the left inversions, right inversions, and split inversions, and then we'll total them up. Okay, so that's basically it. So we'll just piggyback on merge sort, and in the process uncover the split inversions. Okay, so our goal is to implement merge and count split inversions in linear time, O of n, so that sort count inversions will run in n log n. Okay, so remember how merge works. You have something like this, diba? So there could be something like 4, it could be like 4, 5, 1. Oh no, it can't be 1, it should be, let's say, 10. And then here would be let's make this 6, 3, 5, and then 7. So remember, in merge we'll compare the current ones for x and y. So 4 versus 3, which one is smaller? 3 is smaller, so we'll copy that first, and then we'll move y to this one, right? So siya na ang next, so because this has already been transferred. So we'll compare this time 4 versus 5. So this one is smaller, so we'll copy that here, and then we'll move x here. So now we'll compare 5 and 6, so we'll copy this one, and then 6 versus 7, so we'll get 6, and then 7 versus 10, so 7, and then 10 gets copied last. So that was merge, right? So this was the pseudocode of merge. So basically just increment the index of whichever one has the smaller item currently. Okay, so now here's a question. If array A has no split inversions, which of the following is true? Is it that is it alternate, like B has the smallest element, C has the second smallest, B has the third smallest, C has the fourth smallest? So alternate just the left and right? Or are all items in B less than items in C? Or are all items in B greater than all items in C? That B and C was basically the ones that we merged earlier. So B here, C, so merge to D, to this one. So if there are no split inversions, which of the following is true? So if there are no split inversions, it should be that all items in B are less than items in C, right? Because if everything is smaller here, like 1, 2, 3, tapos here it's 4, 5, 6, then there would be no split inversions, right? So, yeah, all items in B are less than items in C. So, for example, if we merge 1, 3, 5, 2, 4, and 6, what would happen? So, okay. So, if we had one, let me change the color first. Okay, if we have 1, 3, 5, and then 2, 4, 6, right? So we know that eventually we'll get this output 1, 2, 3, 4, 5, 6 if we merge, right? But what is actually happening? So first, 1 versus 2, of course, we'll copy 1. But for 1, there are no split inversions here, right? Because 1 is the smallest, so there, and it's in the first item here, so there's no split inversions. And next, 2 versus 3, we'll copy 2, right? But for 2 here, notice that 2 is involved in the inversion of 3, 2, and 5, 2, right? So this one, 5, and then 2. So, we can actually increment our count now, count sa inversion by 2. Okay? Where did we get 2? 2 is the remaining items currently sa left array. So this one and this one. So if we copy something from the right array, so this is the left, so this is the left array, this is the right array. If we copy something from the right array, that means that there should be split inversions being uncovered because there are still items left in the left array, right? And the number of items involved in the split inversions are exactly the number of items left in the left array. So, excluding 1, since we've already copied this down, so there are 2 left. Okay, so plus 2 ang inversion count ta. So, this is done. Now, how about 3 versus 4? For 3 versus 4, we'll count 3. And then, well, we won't update anything because anyway, it's already here in the left part. Now, how about 4 versus 5? 4 will be copied, right? First. And the inversion involved is 5, 4. So, we'll increment this by 1 because there's still 5 left. Okay? So, 4 is done. And then, so 5, 6, we'll copy 5. And then for 6, we'll copy 6. So, in total, there are 3 split inversions, right? So, 3, 2, 5, 2, and 5, 4. So, those were uncovered during the merging of the left and the right subarrays. Okay? So, this is the pattern. So, split inversions involving element y on the second array C are precisely the numbers left in the first array B when y is copied to output array D. So, let's try to draw that one. So, this is how it looks like, right? So, this is the merged version. Let's call this D. This was we call this B, and we call this C. So, split inversions involving element Y. So, the Y here, if this is being copied here, okay, to the merged array D, the split inversions involving this are the items left in B, because all of them are supposed to be bigger right? Bigger sila than y, but they haven't been copied yet. So they appear before y, but they haven't been copied yet, so they're all split inversions. Okay, so that is how we will uncover our split inversions. So while merging the two sorted subarrays B and C, keep count of the split inversions. So when element of second array C gets copied to output D, so meaning the right array, increment the count by the number of elements remaining in the first array B, so the left array. So this is what we mentioned earlier. Okay, so putting all of that together into a what do you call this, pseudocode. So this is how it looks like. So we have the x and y as the pointers for array B and C, and then just compare if bx is less than cy, so you copy bx first, otherwise you copy cy first, and then increment whichever x plus plus or y plus plus. And then if one side is already empty, then obviously you'll get from the other side because there's nothing to compare sa other array. Okay. However, if the cy gets copied first, no, so you increment the count by the number of remaining items in B, or the left array. Okay, so that is how you count the split inversions. Okay, so putting all of that together, that would be this one. So you sort and count the inversions for the left half, the right half. So during the division, you will count the left half, the right half, and then during the merge, you will count the split inversions as well, and then just combine their answers to get the total number of inversions. Okay, so now for the analysis of sort count inversions, the height of the recursion tree is O of log n, because we're just dividing it into 2 each half, log n base 2. So similar to merge sort basically. And then merge count split inversion still runs in O of n, because we're basically just looking at n numbers, so all of the items in the array during the merge, and just checking whether which one of them is bigger, or sorry, smaller, and then we copy that first. Okay, so log n levels, because it's the height of the recursion tree, and at each level you do O of n work, so the total running time is n log n. Okay, so more or less similar to merge sort, because we just piggybacked on merge sort anyway. Okay, so that's it for counting inversions. We just piggyback on merge sort, and then while doing the merging, we'll uncover the split inversions naturally. Okay, so yeah, okay, so that's it for counting inversions. Okay, next we will go to a next problem, which is finding median. You're already familiar with the median, right? So the input is an array of integers, and the output is the median of the array. So do you know what median is? You probably do, right? But before that, so do you know what a Karaya speaker or a Karaya person will tell you if you ask them, "May kwarta kaw?" So what will they reply? They will say median, right? Or if I introduce myself, I would say me John. Get it? Anyway, so median, as you know, is the 50th percentile of a list, and that means that half of the list is bigger than the median and half of the list is smaller than the median. So it's basically the halfway point of the list. So yeah, the middle part. The median is a single typical value that summarizes the list. It's always one of the values. It's not like the mean or the average, wherein it usually is not part of the values. So median is always one of the values, and that makes it less sensitive to outliers. So like for example, the difference between mean and median is that, let's say you have an array of 100 ones. So if we draw this one up, like let's say 1 1 1 that 1 1 1 1, and there's 100 of them. Okay, if this is the case, the mean and the median are both 1. The mean is 1 because the average is just 1, right? And the median is also 1 because you get the half. Anyway, it's all ones, right? So the median is also 1. Now imagine if one of these ones gets corrupted and becomes 10,000. So let's say that this one got changed to 10,000. What will happen to the mean and the median? So this will now become 10,099, right? Ang sum nila. Divided by 100, that would make it about 100 also. Okay. Tama ba? 100. Yeah, about, yeah, kay 10,000 siya. So about the mean jumps from 1 to 100, but the median remains the same because it's still one of the values here, so the middle part is still 1, right? So even if one item got corrupted, the median did not change, unlike the mean that changed drastically. Okay, so you're already familiar with this from your stats in high school, but yeah. So how do we find the median? So the naive solution, the most basic one, is to sort the array, right? Sort the array and then just pick the middle element, because if you've already sorted it, then the middle element is the median. So this could take O of n log n if we use merge sort, which is a good sorting algorithm to use. Can we do better? Of course, because sorting is actually overkill, right? We only need the middle element of the array. We don't care about the relative positioning of the rest of the items. Okay, so as long as we get the middle element, doesn't matter if the rest is sorted or not. Okay, so sorting is doing too much, so we should not sort the array. Okay, so what we'll do is we will reduce the finding median problem into something more general called the selection problem. Okay, so in the selection problem, you have two inputs. You have an array of numbers and the integer k. So your output now is the kth smallest item in the array. So you could have an array of numbers and the number k is equal to 4. So you select the fourth smallest item in the array. So it could be like that. So it depends on the value of k. Okay, so that is the selection problem. Select the kth smallest element in the array. Now how will we use this to find the median? Well, if n is the length of the array and we let m as the middle of the array, n over 2, we will just reduce the finding median of a into selecting a with m being the k. So the mth smallest element, so meaning the middle of the array. Okay, so we can just use this more general version of the problem so that it's more multi-purpose, right? So anyway, so for the selection problem na solution niya using divide and conquer strategy, what we'll do is we will pick a pivot item, we'll call that P, and then we'll split the array, the input array, into 3. We'll call it A sub L, A sub P, and A sub R. Now I'll discuss what this 3 means in a while, but basically what we'll do for the divide and conquer part, during the recursion, we will do the selection in the correct subarray. So either we'll recurse on A sub L, A sub P or A sub R. So basically, we'll select one of the three and we'll choose the correct item in one of those subarrays. So we are reducing our problem space. So from the bigger array A, since we divided it into three, and our recursion will pick one of the three here, and then after that we'll repeat the same process. That would make it faster also, right? So that's the divide and conquer approach. So what are these three subarrays? So given the pivot item P, we will put all items that are less than P to A sub L. So the left part of the array, items that are equal to P, so all items equal to the pivot, because there could be multiple items that match the pivot. We'll put those in A sub P, and then items that are greater than the pivot would be placed in A sub R. Okay, so if this sounds familiar, it's because you've seen something that looks like this before already, like quicksort, right? So it's similar to quicksort, okay, wherein you use the pivot and then you partition the array to put items less than the pivot to the left and items greater than the pivot to the right. So it's more or less the same idea, right? So if we have this array, for example, and our pivot is 5, the way that this would be divided is something like this. So for A sub L, we would put 2, 4, and 1 because those are less than 5, right? For A sub P, we would put this 5 and this 5, right? Because the pivot is 5 and they are equal. And then for A sub R, put the rest because those are greater than 5. So 36, 21, 8, 13, 11, and 20. Okay, so the less than 5s, the equal to 5s, and the greater than 5s. Okay, so given this example, if we were to select the second smallest item, which subarray should we check if we're looking for the second smallest? So if we're looking for the second smallest, we should check the A sub L, right? Because it should be somewhere here. 1, 2, something like that. So we should check the second smallest item of A sub L. So we can reduce select A sub A2 as select A sub L 2. Okay, the second smallest element of A sub L. That would be this one. So we reduced the A's problem to A sub L na lang. Okay, so we made it a smaller search space. Now how about if we were looking for the fourth smallest element in this array? Should we look at A sub L, A sub P, or A sub R? So if it's the fourth, we know that there are 3 here. So the fourth should be somewhere here, right? So 1, 2, 3 here. So the fourth should be the first item in A sub P. Does that make sense? So it's the first smallest item of A sub P. Why is that? Because, again, if you're looking for the fourth smallest, if it's fourth smallest, we know that in A sub L there are 3 already. So the fourth smallest should be the first item or the first smallest in A sub P. Does that make sense? Because if we sorted this one, that would be 1, 2, 4, 5, 5, and so on. So that would be 1, 2, 4, and then this one would be the fourth. But we don't need to sort this one. Okay, we know that there are 3 items that are less than the numbers here. So we just need to select the first item here. Okay. Now, how did we get first? It's because A sub L already has 3. So if we're looking for the fourth and there's already 3 here, so 4 minus 3, that would be the first smallest item of A sub P. Okay, so that's it. Now how about if we were looking for the 8th smallest? So going back here, if it's the 8th smallest, should we look for it in A sub L? No. In A sub B? No. In A sub R? Yes. Okay, so if it's the 8th smallest element, so we know that there are 3 here, so it's not here. There's 2 here, so in total there's already 5 items before that. So it's not here yet. So ikapila siya na item in A sub R, or what should be the rank of the 8th item in A sub R? It should be the 3rd item in A sub R. Again, how did we get 3? So that's 8, but we know that there are 3 items here in A sub L, so minus 3. That was 2 items in A sub B, so minus 2. So that would be the 3rd item in A sub R. Because we know that we cannot find it in A sub L nor in A sub B, because it doesn't it's not enough, right? We were looking for the 8th, and A sub L, A sub plus A sub B only has 5 elements so far. So we are sure that it's in A sub R, and it's the 3rd item of A sub R. Okay, so now we can reduce our selection for the 8th smallest element to the 3rd smallest of A sub R. Okay, so we can reduce that sub-problem. Okay, so yeah, that's it. So putting all of that together, if the K that you're looking for, the rank, is less than or equal to the number of items in A sub L, then you are sure that it's in A sub L. So let's say, for example, there are 5 items. Let's say that there are in A sub L, there are 3 items, and you're looking for the first, or let's say the second item. If it's in the second item, you are assured that it's within the 3 items in A sub L, right? So it's more or less the same. Select A K is select A sub L K. So the rank stays the same because there's no offset yet. However, if you're already exceeding A sub L, so let's say that you're looking for the 5th one, and let's say that A sub B has, let's say, also 3. Okay, and so 3 is already if you're looking for the 5th, you're sure that you can't find it in A sub L because it's not enough. There's only 3 here. So plus 2, can it be found in A sub B? So 5 is less than or equal to the 3 plus 3, which is okay, which is good because 5 is less than or equal to 6, right? So pasok pa siya sa A sub L plus A sub B. If that's the case, then we can reduce select A sub K to just P, the pivot, because we know that everything in A sub B is equal to the pivot number. Okay. However, if it's more than that, let's say we're looking for the 8th item, so we can't find it in the first 3 nor the next 3, so that's only 6 items, right? So the 8th item is plus 2, so that's the second item in A sub R. So we will select it in A sub R, and then K minus the A sub L plus A sub B na sum. So this one basically. So 8 minus 6, which is 2. Okay, so that would be the rank of the item that you'll select in A sub R. So that is how we will recurse for our selection problem. And then after that, we will recurse on the appropriate sublist and then do it again. We will shrink the selection. What we're doing basically is we're shrinking the selection size from the length of A to the maximum of A sub L or A sub R. So whichever is bigger, right? So you're practically reducing the size of the input array each time. Now, the critical question in this algorithm is how do you choose the pivot number? Because it it should be picked quickly, because if you're doing too much for the pivot number, then it would just offset whatever speed gains that you get from the cleverness of the algorithm, right? So you should be able to pick the pivot number quickly and not think about it too much. And it should also shrink the array substantially, ideally in half, but we could accept something close to it. Okay. So how do we pick the pivot number? So the answer is, we'll also pick the pivot randomly, just like in quicksort. So it's the same reason as quicksort, because if we pick randomly, chances are we'll get something, most are 50% of the numbers give you about 25 to 75 split at most, which is already good enough for you to be able to use the divide and conquer approach effectively. So it can already divide it in such a way that it's not unevenly balanced, right? So that's good enough. So you can just pick the pivot randomly, and the hope is we could select approximate median. So not exactly the median, which would give you half, but approximate median. So when we say approximate medians, let's say, okay, let me give you an example. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, 5 is the median, right? Because on the left there's 4, on the right there's 4. But if we get 4 as our pivot, 4 is still good enough, because 4 will give you 3 versus 5, which is more or less still balanced. Same with 6, right? 6 will give you a division of 5 here and 3 here, because 1, 2, 3, 4, 5, and then 7, 8, 9, which is again still good enough. Okay? 3 will give you a division of 2, 1, 2, 3, 4, 5, 6. 2 and 6, which is in some cases still doable, right? And then the same for 7, you have 2 here and then 6. So if you have this splits, basically you can still accept that one, right? Still acceptable. But the bad pivots would be 2 and 1, and then 8 and 9. Those are bad pivots, because if you get 2, there's only 1 here, and then the rest would be 7. 1 versus 7. So that's very imbalanced, right? The same for 8. If it's 8, there's only 1 here, and then 7 on the other side, right? So very imbalanced. And then the worst, of course, is 1 and 9s, because if it's 1, there's nothing here and everything to the right. And then for 9, the opposite. There's nothing on the right and everything is on the left. You have 8 on the left. 8, 0. So you just hope that you don't pick these bad pivots here, and hope that you get the good pivots that are in the middle. So you'll notice that you have 5 good ones and 4 bad ones. So it's basically around 50-50 chance of getting a good pivot. So just pick randomly, okay? Because you have a 50-50 chance anyway, around 50-50 chance. Okay, so that's the reason why we pick the pivot randomly. Okay, so approximate medians are those that I mentioned earlier. So they're values near the median at around 25 to 75th percentile, and using them as pivots will give you a good split still. Okay, not exactly half, but you don't need it to be exactly half anyway. Okay, around 25 to 75 split is still good enough. Okay, and as I mentioned, 50% of these values assure you 25 to 75 split or better. So just pick randomly. Okay, so putting all of that together into a pseudocode, it will look like this. So split array, you have the pivot, random item from A, and then if A sub I is less than the pivot, you add it to the left. If A sub I is equal to the pivot, add it to P. If greater than the pivot, add it to R. Okay, that this takes O of n time, and it could be done in place. O of 1 memory. So O of n time, because you're just going through all items at once anyway. Okay, all items, yeah, going through each items once. So O of n siya. And then in the select part, after you're splitting the array, which takes O of n, so we'll just use the recursion rules that we made earlier. So if k is less than n sub l, we'll select still in a sub l with the same k. But if it's within the pivot, so we'll return the pivot value. And if it's greater than nl plus np, then we'll select in ar, but adjust the rank accordingly. We'll subtract the number of items in nl and np. Okay, so the total running time of this, of course, depends on the quality of the random pivots, because although we are saying that 50% of them gives us a good split, we're still not assured of what the pivot actually is until we run it. So it depends on the quality of the random pivot, ang total running time. Okay, so that's selection. Now, for the analysis, what would be the best case? The best case is if the pivot is the median itself, because that would give us a 50-50 split, half in a sub l, half in a sub r. And that would give you one iteration only, which is, you can find it immediately in a sub p, which is the pivot itself, because the pivot is the median, which is what we're looking for, right? Finding the median. So that would take O of n for the split array, which is already done before even doing the selection, right? So the total running time is O of n just for the split array. That's if the pivot that we chose was the median. How about the worst case analysis? For the worst case, we saw this earlier, that is if we pick the min or the max as the pivot, right? That's the worst that you could possibly do, because that would make the a sub l or a sub r empty, and the other shrinks just by 1. Okay, and it will take n iterations at most, because we're just shrinking one by 1 each time. So it would take n number of shrinks to get rid of everything. So if there are n iterations and O of n time per iteration because of the split array, then it would take O of n squared time, okay, in total. However, this is very extremely unlikely to occur. You're already very unlucky if you get, or if you always pick the min or max as the random pivot mo, okay, each time. So if you sprinkle in some good pivots here and there, then it would not reach O of n squared. Okay, so yeah, this is already in the very extreme case wherein you always pick the min or max as the random pivot. It would take O of n squared time. So that's the worst case. Okay, so best case O of n, worst case n squared. Average case is close to the best case, so that's the good news. It's close to O of n. So just choose random pivots. Okay, so approximate medians as the pivots gives us good splits. So that would give us O of n running time. And for the memory, it's O of 1, because again we could just do the splitting of the array in place, not use an extra array, so that we can keep constant memory. Okay, so that is selection problem used for the finding the median problem. Okay, so that's it. Okay, finally, we'll look at recurrence relations and the master theorem, because it turns out that divide and conquer algorithms follow up a certain pattern. Okay, so you're given a problem of size n. Okay, so that is the original size of the problem, and then you solve a subproblems, so that a being the number of subproblems. So let's say in merge sort you have 2 subproblems, because you're solving the left half and the right half. So a is the number of subproblems, and then the size of those subproblems could be n over b. So because we're dividing it into maybe 2 or 3 or 4, so b is the whatever is the denominator. So if it's half, b would be equal to 2 because n over 2 siya. Or if it's divided into 3, then you have n over 3 basically, right? So b is equal to 3. And then there's also the final combine step or the merge step. If it exists, it takes O of n raised to d. So it could be O of n squared, or if it's constant time, n raised to 0, right? So that is the pattern of your divide and conquer. So because of this, we can actually write the running time equation for the divide and conquer algorithms. So we have the running time looks like this. So the running time for the problem of size n is running time of n over b, because these are the sub-problems, right? And the size of the sub-problems would be n over b. So instead of running time of n over b na lang siya. And then how many sub-problems of this size are there? There are a number of sub-problems. So we'll have to multiply that. A times the running time. Okay? And then after that, there is the additional merge step. So we'll have to add plus O of n raised to d. So that is the running time for the combine. So this is what characterizes the running time of divide and conquer algorithm. So this is the recurrence relation. Okay, so now for the master theorem, given that the running time can be expressed like this, so a times running time of n over b plus O of n raised to d for the merge step. For some constants a, which is greater than 0, so it has to be greater than 0. You can't have, you cannot be solving just 0 sub-problems. So it could be 1, 2, or 3 sub-problems and so on. And b should be greater than 1. So it should be 2, 3, 4, because you're either having it or dividing it into 3 or into 4 or and so on. And then for d, it could be greater than equal to 0 because this could be constant time. So n raised to 0 is equal to 1. So based on the relationship of d, a, and b, so if d is greater than log of a base b, then this is the running time, O of n raised to d. If d is equal to log of a base b, then this is the form of the running time, n d log n. And then if d is less than log of a base b, then this is the running time. Okay, so this has already been proven before, and this is the shortcut to finding out the common running times of divide and conquer algorithm. So depending on the relationship of d, a, and b. Okay, so let's try to look at some of the divide and conquer problems that we've already seen so far and try to figure out their running times based on master theorem. Okay, so for merge sort, the number of sub-problems a is equal to 2. So let's write it down. A is the number of sub-problems, b is the size of the sub-problem. So you have n over b basically, and then O of n raised to d is the merge time. So for merge sort, you have two sub-problems because sorting the original array, you sort the left half and the right half. So you're solving both, right? So you have two sub-problems to solve. And then the sub-problem size is b over 2 because if this is n over 2, this is n over 2 because you're dividing it into half, right? And finally, for the merge step, the merge of merge sort takes O of n, right? Because you are basically putting all items into the original array, so O of n. And O of n is just O of n raised to 1. So our D therefore is equal to 1. Okay? So for merge sort, we have A is equal to 2, B is equal to 2, and D is equal to 1. So if we put that together, what is the relationship of D and log of A base B? Because if you remember, that is our inequality. Those are our inequalities, right? So plug in the values. D is equal to 1 log of 2 base 2. 2 base 2 is equal to, so log of 2 base 2 is equal to what? 1, right? Because 2 raised to 1 is equal to 2. So 1 is equal to log of 2 base 2. So D is equal to log of A base B. And if that is the case, we are going to use the second part. So n of D log n. So we're going to use this one because we found out that it follows this inequality. So n raised to D log n. So going back here, n raised to D log n, if we plug in the value for D, so n1 log n, so the running time of merge sort is n log n, which is what we discovered so far. This is true, right? So n log n siya. Okay? Now, how about for counting inversions? Okay, let me just erase some of the items here first. Okay. Okay, so for counting inversions, it's more or less the same, right? Because it just piggybacks on merge sort. A is still 2. There are still 2 sub-problems that you need to solve. You need to count and sort the inversions of left and the right half. And then B is also 2 because it's half of the original array. And D is still 1 because of the merge time. So it's more or less the same as the merge one. So it's still equal, right? Log of 2 base 2. So we'll still follow the second equation, nd log n. And if we plug in the value for D here, it's still the same. So n1 log n, which is n log n. So merge sort and counting inversions have the same running time because basically we're using the same algorithm. We just piggybacked onto it to do some more things like counting the inversions. Okay, but they're more or less the same algorithm. Now, how about for binary search? Okay, so let me just erase some stuff again to make this cleaner. Okay. So for binary search, what would be the value of our A? So remember, for binary search, what we did was something like this, right? So assuming that it was sorted, so let's say 1, 2, 3, 4, 5, right? So check the middle first, and then if it's in the left half, just look for it here. If it's in the right half, look for it here. So then the value for A is just 1. So unlike some merge sort, it's not 2 anymore. So the number of subproblems that we have to solve is only 1 because we're either looking at the left half or the right half, but not both, right? So we're only narrowing down our search to one of the subproblems. So we're only solving one subproblem and not 2. But the size of the subproblem remains 2 because it's still half, right? N over 2. And for the merge step, since there's no merge step, so that's constant, O of 1. So this would be O of n raised to 0 because n raised to 0 would be 1. So our D, therefore, is equal to 0. Okay? So if we plug in the values for that, 0 log of 2 base 1, log of 1 base 2. So 2 raised to 1 is equal to, sorry, log of 2, log of 1 base 2 is equal to what? 0, right? Because 2 raised to 0 is equal to 1. So those are also equal, and because they are equal, we'll follow the second equation still. And if you follow the second equation, d here will be equal to 0, right? Because remember, d is 0 here. So n raised to 0 will just be equal to 1. So this will be 1 times log of n, which is just log of n, right? So that's why the running time of binary search is only log of n. Okay, so that's binary search. Now for quick sort, how about for quick sort? So the number of subproblems, A, would be still equal to 2, because after we do the partition, right? So around the pivot, we have the ones to the left and the ones to the right, but we still need to sort both the left and the right. So we're still solving two subproblems, right? The subproblem size, however, is a little bit more difficult to describe. B, or the subproblem size, actually depends on the pivot, because we don't know how the pivot will divide the array, because it could be something like this. It could be like heavy on the left and then more on the light on the left and then heavy on the right, or it could be balanced, or it could be like perfectly terribly balanced, like more on the left and then few on the right. So we don't know, because the pivot is random. Okay, so because of this, we cannot solve the running time of quicksort using master theorem, because we cannot figure out the value for B, okay, until we actually run it. So since we cannot characterize it into like a solid number, so we cannot solve the running time using master theorem. So that's the catch for master theorem. We can use it to solve the running times of some divide and conquer algorithms, but not all, because like quicksort, there's an element of randomness. Okay, now how about the best case? For the best case of quicksort, the pivot divides the array in half perfectly. For this one, we could actually analyze it, because we know that it's perfectly in half. So we still have two subproblems, and the subproblem size this time would be 2, because n over 2 is half, so therefore B is equal to 2, right? That is if it's in the best case, wherein the pivot actually divided it into half equally. Okay. There is no combine step, but the partition step here takes O of n, right? So let's just use that running time for the D. So n raised to 1, therefore D is equal to 1. Okay, so if we had 1 here and then 2 base 2, so log of 2 base 2 is still 1, right? So that would still be equal. Okay, so we'll still use the second equation in the master theorem, n d log n. So we'll plug in the value for d here, which is 1. So it's n log n. So the best case of quicksort, as we mentioned, is n log n, and that is if it divides the pivot divides the array evenly, or yeah, like half and half. So n log n siya. But in general, we cannot describe the running time of quicksort, because again, the size of the subproblem, or the B, the value of B, depends on the pivot quality. Okay. Now how about for finding median? Number of subproblems is just 1. because remember that we also did the pivot, and then we either look at a sub L, a sub P, or a sub R. So we chose one of the three and then recursed on that one. So after we recurse on this one, the other two are already discarded, so we don't care about them anymore. So we'll just dive into one sub-problem. So A is equal to 1. The size, however, is again difficult to describe because the sub-problem size depends on the pivot. So since we're choosing random pivots, we don't know what the actual size of the sub-arrays are, right? So again, for the same reason, the running time cannot be solved using master theorem because we cannot be sure of the value of B. Now, how about if we take a look at the best case, just like what we did in quick sort. So if the pivot divides the array in half, then there's only one subproblem, and the subproblem size is half, right? So because we explicitly stated that in the best case. And there is no combine step, but the split array that we did takes O of n to divide it into the three sub-arrays, right? So D is equal to 1 as well. So n raised to 1, right? So plugging in those values, 1 log 1 base 2. Log of 1 base 2 is equal to what? 2 raised to 0 is equal to 1, right? So this should be equal to 0. Okay? And 1 is greater than 0. So since D is greater than log of A base B, which one should we follow? We should follow the first one. So this time we'll follow n raised to D. So if you follow n raised to D and D being 1, naka O of n siya. So finding the median's best case is O of n, just like we mentioned earlier. And the O of n is actually for the split, because if we divided it evenly, we can immediately find the median in A sub P, where the pivot lies. Okay, so yeah, but we can only again analyze the best case of finding median, because we can actually set parameters, or we can set the situation, or we can describe the situation wherein we divide the array evenly into halves. But in the general case, we cannot do that because we don't know how the pivot will divide the sub-arrays. Okay, so yeah, that's it. So that's it for divide and conquer. So to review, we talked about the divide and conquer strategy. So it has 3 steps, right? So divide, when you break the problem into smaller sub-problems. Then the conquer part is when where you actually solve the sub-problems individually, and it becomes so small, so trivial, that it becomes easier to solve already. And then the combine step is when you combine or merge the solutions of smaller sub-problems to form the solution to the bigger original problem. Okay, and then we looked at counting inversions. So basically we just piggybacked on merge sort to count the inversions along the way. And then for finding median, we just used the general selection problem and used that recursion to find the median of the array. Okay, and then we also discussed the master theorem, which tells us the common running times of divide and conquer algorithms depending on the values of A, B, and D, where A is the number of sub-problems, B is the size of the sub-problem, and D is the O of n raised to D submerge step. Okay, and based on the relationship of D and log of A base B, we can just follow the common running times. Okay, so that's it for divide and conquer. If you have any questions, don't hesitate to ask me, and I will see you in the next video.